Okay, in this video I'm going to walk you through Professor Miller's notes on PID control, and of course you should know PID, proportional integral derivative control. Alright, so we've talked about this block diagram several times where you have the controller, the thing that you're building to control some kind of system, and then often there could be a transfer function in the feedback path associated with sensors or some other reason for having an H of S. Okay? So, we've talked about this several times. You have a reference signal, okay, R. This is in the Laplace domain, so R of S. All right, and you take the output as measured by the sensor, or there might be something that's proportional to the output. Anyway, you have a Y hat, and you can view this as the control error signal. All right, so there becomes a matter of definition when you look at steady state error if you have a transfer function in the feedback path. All right, so we'll have to take a look at that kind of case if it comes up in the problems that we look at. All right, so by that I mean normally you would think of the steady state error as being this error function as being E, which is the reference minus the output. But if there's something in the feedback path, then you have this E, I guess he's calling it A, which is R of t minus Y hat of t. So Y hat is probably related to Y through H of S, but not necessarily known to be exactly the same thing as Y. All right, so we're trying to control a plant or a process or something that we're trying to control. Hopefully we have some sensor so we can measure the output, all right, and turn that into some electrical signal that we can work with. All right, so PID controller, we can look at the control. All right, so U of t, think of that as just a signal. It doesn't mean unit step at this point. It's just a signal. And it's going to be some constant Kp times Ea of t plus a different constant Ki times the integral of that error signal. And the integral goes between, when you turn the system on at time 0 all the way up to time t. All right, and then it turns out sometimes we want to add some control element that looks at the rate of change of the error signal. Okay, and because we have this rate of change in there, we can possibly react more quickly to a change in the system dynamics or something that comes up that lets us shape the step response in an additional way because we have a third knob to turn. Okay, but of course, adjusting 3 parameters is even harder than adjusting 2. Okay, so sometimes people will try to just do PI control and then throw in the D if it looks like they need to sort of improve the response in some way. All right, so next we just take the Laplace transform of everything. All right, so that would be Kp times Ea of S, and then the 1 over S, the Ki over S is the part that shows that this is the integral, and then of course for a derivative you get S times Kd Ea of S. All right, so this is the Laplace transform of, I missed the error signal. This is the Laplace transform of U of S. Okay, so you can think of this in terms of block diagrams. All right, so you have a proportional path, an integral path, and a derivative path that sum together to give you the control signal. All right. All right, and that's what's going to apply to the plant. All right, so parallel paths in a block diagram gives you a single block diagram unit that looks like the sum of the 3 components. All right, so there's a PID control file in some of the content that comes in, I think that's module 7. We'll go over that in a separate video. Okay, so one of the tricks I've told mention this, it's sort of an art form to get the time domain response to behave in the way that you want. Okay, so what we do is we look at adding a PID controller or a PD controller and look at the root placement. Remember, when we say root placement, what we really mean is poles. And in the examples that we're going to start with, these poles are going to be from a dominant second order system pair. All right, now I'll discuss what I mean by dominant at some later point. Okay, so it's good to have some sense of what each knob is going to do in terms of step response parameters that we are familiar with for shaping the response. Okay, so we've talked about there being the idea of rise time and overshoot and settling time and steady state error. Okay, so you should have some idea of what those look like. So what we're going to do is we're going to play around with some examples, and we're going to demonstrate this table in terms of how you would tweak parameters to shape an output response. Okay, so if we increase KP, then you might think that makes sense, that increasing KP means you're noticing you want to add gain to the error signal, so you're forcing the system to act more quickly. All right, so that would decrease the rise time. Okay, so if it's acting more quickly, it's responding faster, the rise time is smaller. Okay, but when you add more to the system like that, especially if a system has some dynamics and inertia and those kind of things, that's going to tend to increase the overshoot. Okay. Increasing KP also has a small change on the settling time, but not as dramatic as, according to this table, not as dramatic as what you would see for rise time and overshoot. Okay, and also increasing KP, if there's steady state error in your controller design, increasing KP would tend to make that smaller. Okay, so if you add integral control by increasing KI, the table reports out like this. You would also decrease rise time, you would also increase overshoot, you would increase the settling time because you have this extra integration step. Okay, but the huge advantage for integral control is that it offers the possibility of totally eliminating the steady state error for a step response. Okay, so that's a key thing to remember. All right, then there's other parameters that we'll explore. We're looking at increasing KD. Hopefully we'll see that has a small change on rise time. It decreases the overshoot because it gives you an idea of what the error is doing a little bit quicker, because you're looking at the rate of change of error, not just the absolute error. Okay, that can decrease the settling time, and typically this would not have any change on the steady state error because of the S term that shows up in the derivative. Okay, so that's the general idea, but what you need to do is play around with examples to try to, it can be solved by trial and error, but there's also some more formal ways of solving the problem of tuning your controller. But what we're wanting to do at this point is get some intuition about what happens as we change pole placements. Okay. So next, I wanted to talk about different forms of a PID controller that are described in the S domain, because we're going to work our way into something called the root locus. All right, and so with this, what we're doing is we're establishing a relationship between the three parameters, and we're changing it from 3 knobs to turn to only 1 knob to turn. All right, and hopefully we do this in a systematic way. And we do that by rewriting the transfer function in a certain way. Okay, so if you had a PID controller, you can find a common denominator, and it would look something like this. And then you can factor that, and you would get 2 0 locations and a pole at the origin. When I say pole at the origin, that means at s equals 0. Okay, so that's the transfer function for the PID controller. You can think of it as adding 2 zeros, okay, or having 2 zeros and a pole at the origin. All right, so then we'd have one parameter k if we fixed z1 and z2. Okay, so you see what we did here. We divided through by, let's see, we divided through both sides of the equation by kd, okay, and here's the equation we looked at. Okay, divide through by kd, you get a kd that you can factor out, and then these show up as changes in coefficients that are normalized by kds, or I'm sorry, by kd. And then once you have that, you can find the, use the quadratic equation to get expressions for z1 and z2. All right. Okay, so my main point of that is I'm thinking it's hard for you to put all this together at this point because you haven't seen root locus yet. But what we're going to do with the root locus is we're going to take a look at pole locations as a function of one knob, k. All right, so this is the full PID controller transfer function. You could set some of the knobs to 0. All right, so if I had the PI controller, that would mean the KD knob is set to 0. All right, if I wanted a proportional derivative controller, the KI knob would be set to 0. All right, so I wanted to set you up for what we're going to do with root locus a little bit later. All right, so hopefully this helps you get an idea of what we're trying to accomplish with the PID controller. And next, I'm going to walk you through a video of exploring a practical problem and how to interpret that in the realm of PID control and step response.